All right, so I think we are live, at least. Yeah, we should be now.
Yeah. Yeah, just got the notification. We're live.
Awesome. All right, so let's wait a few minutes for people to join. So today we will be talking about Polygen, which is a library created by Robert. And yeah, if you can give us an introduction to this library
Sure.
and what does it do?
Yeah, so generally, the Polygen is a library that allows you to run WebAssembly in your React Native applications, but with a small caveat that it is not being interpreted, but instead we are compiling the WebAssembly modules to C code that is later embedded in your application. So this allows you to have the WebAssembly modules essentially have near native performance and be just embedded as a regular native code in your application. So the goal of this library is to close the gap between web and React Native. The origin of the library started in our effort to bring one of the game engines that is being implemented and is running pretty smooth on web. And the goal was to move it and like support a React Native version. And currently the ecosystem, the default approach and the only one is that if you want to support like external native code, you need to create turbo modules, which is fine and probably is currently the most performant way. Maybe except Nitro modules, obviously, which have the tendency to be even faster. But the default way is to create turbo modules. And this creates a separation that on web you use WebAssembly for native code, and on React Native you're using turbo modules. So you have two pieces of code to maintain. Even though if you are not even like the developer of specific library, for example, if you want to bring a database or a crypto library like bcrypt into React Native, even though you're not source code contributor to bcrypt, you need to create a true module for it, which may or may not be easy. So the goal is to just have your WebAssembly, put it in your source code, run Polygen that does the magic, and essentially you'll be able to use it just as in web using the web APIs for WebAssembly. So essentially and ideally, any code that runs on web regarding WebAssembly would run on React Native. That's the goal of our library.
Wait a second, I have a question here. So you have a game engine and you wanted to move it to React Native, right?
Yeah.
So why haven't you compiled the game engine to C++ turbo module? Why do we need to have this intermediate step? Did you have the access to the source code of the engine, or you only had the WebAssembly?
Yeah, I mean, the game engine itself is written in JavaScript, but it uses like Rust and C++ modules for like math, physics. Yeah, so a small spoiler. My goal in this stream was to actually create a WebAssembly module using Rust and run it live on React Native. But there's a very small caveat I couldn't do on time. So I promise on the next web stream or like for the next version, we'll be doing the Rust WebAssembly module running React natively. So not yet. We are very close though. So yeah, unfortunately, Rust confirmed, but not yet to be run. Yeah. And
So maybe
on your
Mariusz,
backlog.
yeah,
okay.
obviously, yeah. And yeah,
Go ahead with the question from Mariusz.
Yeah, so you asked like, why did we do the intermediate step, right? Yeah, because the JavaScript, it's not that the game engine is like a big block of native code. It uses native components, which were compiled to WebAssembly. And those WebAssembly artifacts were provided usually by the library authors. So what the game engine developers had to do was just to use those WebAssembly modules and use them essentially. They didn't have to get into the trouble of how to compile those modules themselves from like Rust, Go, Swift, or whatever, like maybe C with Mscript. And this is not that easy. But if the library, like the dependency provides it's like just like simple install and usage. So there's no any additional steps there.
I know it's kind of like a guessing game now, but can you imagine what can be the difference between you compiling WebAssembly to C native codes and using it in React Native versus compiling the thing that was compiled to WASM directly to Turbo Module? There would be like a huge difference, or it's basically the same?
I think Oskar can answer, because when we are helping with bringing the web engine to React Native, we had two paths. One path was to experiment with native compilation of WebAssembly, and Oskar was doing the second path to like as a sort of a baseline for performance. So he manually created turbo modules for those dependencies. And maybe let me ask Oskar, how was the experience doing so?
Yeah, so that's something I wanted to maybe stop at for now, just to discuss this approach of actually manually going from C++ module, and we can actually show the module with Bring this way, because it was an open source library that's now also an open source library. So we actually open source two of those bindings from C++ in that case through a turbo module to React Native. And like talking about performance, like this was a bit more performant, obviously, because we were like, not going through WebAssembly. And on top of that, we could also like out of the box leverage some features. If the library supported, for example, multi-threading, it was like just one defined, like use multi-threading or something. And then you pass how many threads you want to use, and it automatically worked. In WASM, it's not as simple as just leveraging the built-in way of multi-threading, but it's possible also to achieve. So maybe I can share the screen and actually walk you through. Let's do this one. All right. So the library, it's React Native Basis Universal, and Basis is the Basis Universal is a GPU texture codec, which is a C++ library, and these are just the bindings. And what's tricky about like creating the bindings for such a library is that you have to at first be familiar with the library. So it's not just that you can, at least we didn't find a way to like auto-generate the codegen spec and then auto-generate the implementations. So for example, for Basis, I'm not sure which technology, I think it was Mscripten that they used to create those bindings from the C++ code to WebAssembly. Do you remember, Robert? Was it Mscripten?
Yes, I think so.
Yeah, so like they already had this layer of exposing C++ code to JavaScript, like through WebAssembly using Mscripten, and like it wasn't working with React Native whatsoever. So what we had to do is, as you can see, like the end goal was to just replace this import. So from like basis universal, you could replace the import to @callstack / React Native basis universal and have your app like working in a totally new environment inside of React Native. So in order to achieve that, we had to, for example, create a JavaScript spec, which was pretty big. And like you had to understand at least what's happening inside of this library. So it's not just that you can simply generate those bindings to a CodeGen spec, and then it happens automatically, like it is with WebAssembly. Like you have to do a lot of manual work, and the bigger and the more complex the library is, the harder it gets to create those bindings. And it's not the case with WebAssembly, where like everything is handled for you if you go through this Polygen layer. So so I will quickly just
highlight. I want to highlight one thing, that you here created only the the low-level spec thingy, and usually, like in the example of the engine we had to bridge, was that they were using, first of all, WebAssembly, but they also used the like generated JavaScript bindings that were like simplifying the interface. So like they had some sort of object-oriented interface for it, kind of.
Exactly.
And first of all, you need, in this case, you need to create the specs and bridge the code for React Native, and then you need to create those wrappers yourselves, which were generated in case of WebAssembly usually.
Yes, that was also a tricky part, because we had to like recreate the same interface using the CodeGen spec, which was not the easiest task if the implementation was, for example, based on classes. Then we had to like pass in, as you can see, some OpenQ native handles so that we could attach native state onto those objects. So it was a lot more than just bridging those calls. It's not just like one-to-one call that you can map. You have to create the whole structure of the API that was before generated by mscripten. So let's quickly check how the C++ code looks like. So you can kind of see how much work it is. So here is, for example, some kind of an encode function. And most of the code inside of the functions were actually from the wrapper, from the mscripten wrapper. So we could just, use it if we take the correct types, object types. So for example, we pass data through array buffer, which is supported inside of JSI. And so it was a lot of code getting this bindings to work properly. And now on top of that, there is also the maintenance. So if somebody in the basis universal library changed some interface or deprecates an interface and creates a new one, we will have to create a new function inside of the CodeGen spec, and then generate the new function and implement it. So whenever some changes to the library happens, we also have to do something on the library side with the bindings. So yeah, like a few hundred lines of C++ code, which was efficient, that we could create those bindings, but it was definitely a lot more work than just generating bindings from WebAssembly to React Native.
Any ideas where the performance difference comes from? Like, even if you will compare single-threaded code here and there, WASM is single-threaded, if I remember correctly. Where does the difference come from? What's lost in the translation, let's say?
I think that Okay, so we didn't do extensive benchmarking yet because we are too early in development, I would say. But as for WebAssembly, it's a binary target. So it is aimed for like to be a common layer between different architectures. So right now, people like to call it just an advanced calculator because most of the instruction set is operating on numbers plus you have some memory. And yeah, you can compile it back to C, and it's like obviously it won't be the C you wrote from, but it would be like a very low level generated code. But the compiler can actually do some magic there and increase the performance. But the main performance cost comes from the layer of abstraction and maybe the platform independence thing. So I'll answer the question very shortly. Just to continue with it, is that the performance impact comes from the fact that when you compile, like the case Oskar shown, like basis universal, when you compile it for maybe RM on iPhone specifically, you have some constraints and guarantees that the compiler can work on and optimize code even further. But when you target WebAssembly, you need to remember that it's like a sandbox, which is can impact your performance, but you get this benefit of it being a sandbox. So it's a good way to actually isolate some code and ensure that it doesn't poison your environment or do some harmful things. But yeah, even if we compile it back to C, I think that WebASM to C tool benchmark, which we are actually using the tool, it reported that in the best case scenario, the performance impact is around 5 to 7% optimistic. So that's not too bad coming from the fact that you use the same code essentially for web and native, and you don't need to do any branching, no maintenance. So, and it will get only faster because the WebAssembly spec is getting more and more complex, I would say. So it covers more and more things like garbage collection, reference types. So these things that, because if WebAssembly supports them, source languages like Python, Rust, Go won't have to lower them so hard. So the abstraction of WebAssembly will be higher, which will obviously contain more information, and it will leave more room for compiler to optimize because it will have more data about the code rather than just simple additions and math operations.
Regarding all our questions, what you want to achieve?
So,
okay, I can take this one. So the library, the React Native Basis Universal, it was a wrapper, as I said, for a Basis Universal GPU texture codec. So it could, for example, encode a PNG picture into a KTX file, which is an optimized version of a file that you can use inside of the game engine that we worked on. So it was mostly doing a lot of math inside the library.
Exactly. And the goal is actually to make the cross-platform even better. So you don't have to worry about Turbo modules. You can think about it if we skip the part that WebAssembly is currently a bit limited, but it will get only better. You can think of the WebAssembly modules as an alternative to Turbo modules, because you write Turbo modules to introduce native features, native APIs into React Native, and the same more or less could be done with WebAssembly. So right now it's not that far so that it can be done, but eventually you could think of it this way. So a sandbox environment to introduce native operations to React Native.
But only native operations that are platform independent, right? So no calls to, let's say, UIKit or I don't know, some other iOS library.
Unless like there is some spec to WebAssembly for like SSI highly adopted. But there's like, this WebAssembly system interface. So it's like a generic interface for interoperability with system. So it provides like a basic contract like API for maybe file system operations. The same could be done, maybe not for UI, or like basic stuff like notifications and whatnot. So there could be like WebAssembly mobile interface that just abstracts away those parts and is provided somewhere. But yeah, for such stuff like UIKit, it would be very hard to represent in WebAssembly. So yeah, I wouldn't aim for that. You would be better off with Nitro modules or Turbo modules.
Yeah, that was what I thought. So it's mostly for platform independent logic, same where you would use, for example, C++.
Yeah, exactly. So as an example, maybe, UIKit is a kind of platform dependent thingy because you cannot run it in browser. But as an example, you could have a cryptographic library running in WebAssembly because those are usually cross-platform. It's like not related to the UI at all. The same with like maybe databases. You could run, I think, SQLite in WebAssembly. So usually anything that is UI irrelevant, so like headless, is a good candidate that could be done in WebAssembly at some point.
I would like to quickly address one of the questions that appear on the chat. Ola asked if you have a regular React Native app and Turbo modules, can you just use WebAssembly? I think it's even better because if you have a React app and you have a WebAssembly on web to do some calculations, you don't have to port it to Turbo module. You can just drop in to React Native and work it there.
Yeah.
It doesn't work the other way around, right?
Yeah, exactly.
But if you have Turbo modules, you can also just compile them to WebAssembly, like the extra stuff. You have the choice. You can implement them in Turbo as Turbo module or Nitro module, or just keep it in WebAssembly format.
Yeah, exactly. So just like a simplification of migration path, really. You can think of it like that. So it depends if you are coming from web to React Native, which is one thing, because usually if you are needing native performance, the only choice you have is WebAssembly because that's the only thing that browsers support. And that's one of the migration paths we actually targeting. So people coming from web with advanced operations on WebAssembly. And the second thing is, I don't think there is a case. Maybe if you are working on specific platforms that support WebAssembly, and you need to maintain multiple Turbo modules, then WebAssembly can help. If you are like without web application, only React Native, I think right now Turbo modules should still be the first choice. But yeah, I think there's some cases where different platforms could be more like easy to use with WebAssembly, I think.
So when should I reach for this library? If you would describe it so the audience can understand better, when should they go from Turbo module to WebAssembly module?
So the simplest answer is that if you are already having like a WebAssembly modules on web and you're thinking of mobile application, that's the go-to choice, I would say. That's the main goal of the library. The second thing is if you are targeting very different platforms and there may be a requirement to support web so that you don't have any other choice on WebAssembly if you're targeting anything web related. So there is that. And lastly, I would say, if you're in need of a native module that there's already a WebAssembly module for, let's imagine maybe cryptography library. So if you need it in your React Native app and you do not want to, write it yourself or whatnot, there's all of that. You just paste the WebAssembly module and it gets compiled and it just works. So mostly for simplicity, cross-platform support, and ease of use. Because if you're given WebAssembly module, you don't need to do anything really. You don't need to write any native code, so it just works all of the box. So that's the main goal. But if you're, hardcore performance targeted oriented programmer, you want to squeeze every last, operation in microsecond, whatnot, or you're only targeting, React Native, iOS, and Android, then maybe you don't need it all, because you're better off using Drupal modules and Nitro modules probably.
You said that WebAssembly is the only way to run high performance computation heavy code on web browsers, right? What do you know what happened to ASM.js?
Yeah, it was. Correct me if I'm wrong, but is it like the precursor of WebAssembly? So that's the first steps of introducing performant operations, let's say mathematic operations on JS, that eventually evolve into WebAssembly. So it's like a kind of precursor for WebAssembly. But I'm not tracking it. So correct me if I'm wrong, if it's still alive. But I tend to believe that it's dead right now. The WebAssembly took its place, but I'm not sure really.
And you said that we basically can compile any application, program in any programming language to WASM, like Zig or Rust or C++.
Not yet.
Can we do the same thing? We will be, right? Like with Polygen, maybe not yet, but theoretically there is like Rust to WebAssembly.
Yes, but some languages like Python cannot be compiled yet due to some limitations of WebAssembly. I think it was like, obviously there are dynamic languages, but there's stuff like garbage collection, reference types, which I mentioned. So if they get added, more and more languages can be compiled to WebAssembly. Yes, that's true.
But cannot you compile the Python interpreter in C code to WebAssembly, because the interpreter doesn't use, I think, ref types or garbage collector. It implements there, right?
Yeah, exactly. There's like, you can compile actually Hermes and JavaScript core to WebAssembly, so you can have JavaScript engine running on WebAssembly in your browser. So there's that.
I think Linux as well. There were some people who compiled kernels.
Yeah, if I remember correctly, some mad lad actually created a Linux JS so that you open some kind of OS compiled to WebAssembly, which is nuts. So if that ever runs on React Native, it will be, just imagine the possibilities, like having your Linux on iPhone. That will be mad.
I have a question about, so what would be the case, the use case if I want to start a new module? When would I pick, like, I want to write, let's say, a module that calculates the nth number of a Fibonacci sequence. When would I reach for Polygen in that case?
So because it's like mostly mathematic related, it's a good candidate, because there's not much of the outside stuff going on. So that's a good thing to check. Depends. Do you need web? Because maybe you don't need it right now, but you never know if you won't need it in the future.
Yeah. So if you want good performance, like really fast module on web, that's where you would reach for Polygen.
Yeah.
Okay. So
and think I can show you a demo of it, but I'm not really sure if that will be that easy. So let me check. Let's just
Mike's
wait.
here.
Oh,
Hello.
hello.
Hi, Mike.
Hey, Mike.
Mike.
You're just in time.
I wanted to ask you something, Mike. I've heard last time you were doing some Vim podcasts, and I wasn't sure if you being late is correlating or not. How was the journey?
Yes, I was trying. Yes, this is the time for this annoying joke where I say I was trying to exit Vim this whole time. Ha 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 ha. Actually, I'm sort of stuck. Turns out having this type of keyboard is really helpful, but I was away. So I would say my Vim learning journey is not going as fast as I wanted, but I'm definitely committed. So we'll see.
Good news is that you made it perfectly for Robert's demo about like Polygen. So
yeah. Now I can escape. So I need to do it.
Nice. So I made it just on time.
Exactly.
Yeah. I have one more question before we jump into the demo. So there is this static Hermes stuff that's going to be out soon. So how do you think the performance would compare in that case? If you want to, let's say, implement the same module that calculates the Fibonacci number, and like you can compile it with static Hermes, and how would the performance compare there?
That will be actually pretty cool to measure, because if static Hermes compiles to native code, you can actually compile it back to WebAssembly and have it running on web. So you can have really performant JavaScript on web, which does not have static Hermes. So that would be nuts. Just imagine the possibilities of writing native modules kind of with static Hermes if there ever will be some kind of FFI. That would be just you won't even need to touch C++ anymore, mostly, obviously. So yeah, the future is bright. I'm really excited, and I cannot tell you yet what kind of performance difference it is, but it's a really cool thing to measure one day. So yeah, that's true.
Yeah, I was thinking like more about your expectations, as you're like a C++ expert with Mariusz. You know how the stuff of static Hermes is going to be implemented, so you can kind of based on the approach kind of guess how it's going to be the performance compared. I'm not asking about numbers because you have to measure to get the numbers, but based on the approach, like what would be your guess of, would it be faster, would it be slower? Like but the idea of compiling it back to WASM is actually interesting if you have JavaScript, really fast JavaScript running on web, a native JavaScript kind of.
Exactly.
That would be cool.
Yeah, it would be cool if we could just skip the script and call it Java, but it's already taken. But that's a good question, really. Yeah, that's a really good question, really. Like, static Hermes has probably some more context for optimizations than WebAssembly right now because it's very low level. JavaScript is longer in the market, so there's like more information on how to optimize it. But yeah, I'm not sure. We are compiling it back to C, and like C compilers were like here forever. So maybe it's hard to say because
I think maybe static Hermes has a little bit disadvantage here. JavaScript is not very heavy oriented for math, and if I remember correctly, WebAssembly wants to introduce like vectorization and SIMD primitives. So maybe this is the only way where WASM or like WebAssembly can be faster.
Yeah.
But that will be really tough and nice to see benchmark in the long run.
Also, JavaScript is single-threaded, so like WebAssembly kind of as well. There are some like extensions to the specification, but if it ever goes like standard one day, then you would be able to outperform single-threaded JavaScript, I think.
Okay. And how does it work in React Native? Like if WebAssembly is single-threaded, and let's say I call JavaScript, like I call the Polygen function from my JavaScript code. Does it block the JavaScript thread? Does it use a separate thread? Like what's the specification around this, and how does it work?
For most of those questions like that, the first answer I can say is that it works just like a turbo module. So if you have a heavy turbo module method, it also blocks the JavaScript. So the same goes with WebAssembly. So right now, if you like, do some crazy operation in WebAssembly and call it on your JavaScript thread, it will block, because that's what spec says, and we cannot really do much about it. The default way to work around it on web is actually to spawn a worker. So it's like a kind of a separate thread that runs the WebAssembly and just communicates back and forth with you. So this way it does not block. But right now, React Native does not support workers. So as of now, it would block the thread, but we are thinking about some solutions to offload it to a different thread, but in a way that does not break the spec that hard, or so it's even like a transparent for you. So yeah, we are aiming for such kind of optimizations before like stable release of 1.0. So yeah, that's one of the things we are actually working heavily on.
Yeah, that's interesting. Thank you for explaining. Okay, last question before we jump into the demo. If you could like walk us through how does it actually work? Like, from the WASM code.
The best question before the demo, like how does it actually work?
Yeah, how does it work? Like what kind of magic do you do that it works?
I just wanted to say magic, but you actually used it. So so the process is that you just paste your WebAssembly modules somewhere in your source tree, and you have this Polygen tool which actually looks for those WebAssembly modules and uses the wonderful WebAssembly-to-C tool from WebAssembly binary toolkit, which is a wonderful tool, and it actually generates C code that there is some missing functions there that you need to implement yourself. So if I have a Fibonacci function within a WebAssembly module, it will generate like two big files for this module with all the boilerplate and abstraction of WebAssembly, and it's expected of you to implement some of the methods. That's what Polygen does. There's this like part of native WebAssembly runtime, like management of memories, tables, and whatnot. And this is handled by Polygen runtime as well. So then when we have this code, we are actually generating the glue code that connects this generated low-level C code and implements a turbo module on top of it. So we are actually let's say implementing some kind of turbo module for this code. So we are actually bridging, the types, the methods to JSI, so it's visible in JavaScript. And yeah, that's actually it. That's the hard part, but that's it. We are actually doing some, small fix here and there so that you're able to use web APIs. So you can, even though the WebAssembly modules you paste in the source tree need to be, pre-compiled, there's like some kind of allow list. You only can run WebAssembly modules you specified ahead of time. But we also have this kind of trick to support fetch so that your web code works out of the box. So when you fetch some WebAssembly module from somewhere, we are not interpreting it, but we are looking in the cache in our application, which of the pre-compiled WebAssembly modules has the same checksum. And we know that this WebAssembly is this one that is pre-compiled, and we actually run it. So even though there is some overhead of downloading this WebAssembly module, there is no overhead of interpreting it. So this is mostly for simplification of migration from your web code to this one. Yeah, just as you would write the code yourself as a turbo module, plus some abstractions for WebAssembly web interface. I'll try to show it all in the quick demo, I would say. So I'm not sure if this answers the questions or even raises more questions.
Follow-up one. What happens if the checksum doesn't match? Like if you want to download a newer build, which you haven't precompiled, are you falling back to interpretation?
No,
or you just throw?
It just throws with an error that you probably forgot to paste, or paste the WebAssembly in the source tree, or you pasted it but you forgot to regenerate the native code, so that you are not allowed to run arbitrary code in this way. So if it doesn't matches, then you cannot run it because it's not there simply.
Okay,
Yeah,
show us the tool.
I think like it's also important to mention that like on the web we do just-in-time compilation when you load WASM module, and like why is it not a thing on mobile? Why can't we do that?
So you can. There is this React Native WebAssembly that does just this, but it hurts performance really. So I think it's the most is the best way to run WebAssembly without any limitations, except of performance being interpreted. So if you want to have all of the features of WebAssembly, and you do not care about performance, this can be a good choice. But we were thinking whenever we can do better performance, because that's one of the main reasons to even go native and not write a turbo module, is you need performance. So yeah, you just let me think about it, because
Yeah, let me add to this. So from our research, when we work on this project that we mentioned before, iOS and Apple rejects apps that do just-in-time compilation.
yes.
So
Yes.
that was like the main reason. So there is like React Native WebAssembly, and it works in development, but maybe the apps with this library were never shipped to App Store, or maybe Apple didn't catch this time. But like having your app with a library that can be in the next release rejected like isn't the best idea. So that's why we also do the pre-compilation for performance and also for compliance with Apple rules that you can only that you cannot do just-in-time compilation in your apps.
So there's I actually forgot about it, because there's like 3 ways you can run it. The first one is the interpretation, and I think it's allowed in App Store, but it's slow. Most of the WebAssembly runtimes actually go for just-in-time compilation for performance reasons, and this won't go on App Store unless you're using Safari, but we cannot use it. And the third one we are actually doing is ahead-of-time compilation. It has more limitations, but the performance is the best we can do, we can get. But there we are actually designing Polygen in a way that in the future, like in the version 2 or 3.0, we'll be able to have multiple runtimes you can select from. So if you do not care about iOS, with the same interface, you will be able to run the WebAssembly modules with just-in-time compilation. This is the long-term goal, but we are thinking of doing it similarly to GDSI. So you will have this WebAssembly runtime interface. Or you can do it ahead of time compilation, you can do interpretation, you can do just-in-time compilation, whatever you need. And it's up to you depending on your requirements, limitations, and whatnot. So right now, our main goal is performance ahead of time compilation, and where it gets us, we'll see in the future.
Okay, thank you for answering. So I won't stop you anymore. Go with the demo.
So now I have to do it. It's okay. All right. So let me know if you can see my screen.
Yes, we can.
Okay, cool. So yeah, this is the project we are talking about. If you just joined the React Native WebAssembly called Polygen right now. So this is our WebAssembly toolkit for for React Native.
Hey Robert, you need to star it. You didn't give it a star.
What do you mean?
Start the project. Star, like the GitHub star.
No, I don't star myself, my project. You don't do this.
It's under Incubator, so it's okay.
Okay, then I will just start.
And everyone watching should also press a star. There.
And
Yeah.
if everybody does that, you will have 500. So
Exactly. Cool. Yeah. So this is very early prototype, but let's maybe show you some very simple demo. I won't go through whole README because this is very specific for some cases, and we'll just go YOLO and do some very simple application. So right here, I have my editor with my React Native Polygen, and here I'm working on example apps. So I'll just show you how you can bring your WebAssembly modules to React Native. But before that, let's just try to run it on the simulator and see if everything works. Hopefully, I hope I didn't break anything. So yeah, this is the Xcode that just contains this workspace, and let's see if it compiles. Right now, I'm just running the project out of the box as it is in the repository.
Can you make the font bigger a little bit?
Sure. Let me try to do this. Yeah. Like code does not matter yet, so yeah, soon. And yeah, I need to start the methods. It works. Yeah, so this is the example application. As you can see, I stole it completely from Oskar's app because there's still bottom-text example here.
You should change at least the title.
Yeah, I just say that I completely stole it from your app because yeah, it worked. So the credit where it's due. At least the people know that they stole it. So we have currently 4 examples here. I can show you what they look like in source code. Maybe I can increase the font here too. So kind of trick.
Yeah,
No.
I don't think WebStorm supports it. Like you have to go to options.
Yeah, let me just quickly. Oh, there is a shortcut, but it is a complicated one. Okay, let me try. 0. Okay, maybe this one. Yeah, it works. Nice. Okay, so the first demo we can run is let's see, maybe fetch example. So here, let me maybe just hide those. Here we have this simple React component that loads a module. Please ignore those TypeScript errors because I was hacking around with type definitions, but it just works. It's just like the issue with the WebStorm type information. So what we do here, if we have, is that we have this callback for loading the module. It fetches the module from the server, and then we can load it by pressing a button, and we can see what it exports. And let's see what it does if I do not run the server and try to run it. It just reminds me that I should run the server. Let's see. Yeah, the network request failed, so that's expected. So let me run the cd example STC Python 3M HTTP server.
But
So
you can
now
use
we
Metro. Metro is also saving files. I just have to use different port, I guess, right?
Yeah, but that's the case when you want to actually fetch it from some kind of server. So
okay.
this is like simulation of loading the WebAssembly from like remote location, which is not part of your bundle. So
Okay.
right now we are serving the mock server that returns the module. So we should be able. Oh, this is not it. This is it. Right now we fetched it and it calculated the checksum, and you can see that it loaded the module, and we are able to see that it exports a Fibonacci method, which is a function, and some kind of memory named memory. So using fetch works, and you can see I didn't anywhere in the code, I didn't even reference the module we are using, because it is actually this module, but I just fetched it and it works. I didn't reference it anywhere, so the Polygen just make it works.
But how does it work? Like with the pre-compilation step we talked about before, like you have to have it linked to your app, right? Or
yeah, just because I have it here, it's part of my application. So there's some kind of tricks that you need to be imported, but because I just pasted it here, which I will show later on, that I create a new module and run it here. So just because it's here, when I do Polygen generate, which we'll do later, it's part of the application. We computed checksum, and because this is exactly the same module that we fetched, and the same that it is in our application, the fetched just works, and we can do like compile streaming and whatnot.
So what's the use case for this if you have to have it precompiled? Like, because maybe I don't understand it.
Of course, this is not the way you should use it. This is the way that you can copy your web code and it runs in React Native. So this is like the first step of your migration journey. If you just paste your WebAssembly modules into the source code, and you have this web code that uses, compile streaming, uses fetch, it's not ideal. It, does this round trip of network requests, it downloads it, but it just works for you. And you can then later on focus on removing it and make it more performant. So this is like the goal of it is to make the way you use it on the web for React Native. That's the main goal.
Okay,
so wait, you're not interpreting.
No.
So where is the? You said. Sorry, Oskar. Continue.
Okay, go ahead.
So, like, you haven't done anything. You're telling at the very beginning of the stream that this is compiling to C.
Yeah.
But you just pressed play. Like, where is the compilation step? Like, what's
I'll
happening
just show
under
it.
the hood.
Of course. Okay, I just wanted to show how it looks so people can know what we are talking about right now. But the whole cycle, I can show it to you right now. I'm thinking whenever there's some maybe simple example we can discuss, but actually collapse the styles. It's not that really interesting. Okay, so how about we are doing some new module live. So you can see how the process of moving and creating WebAssembly modules look like. So to do this, I will be using assembly script. In the next stream, we are having about Polygen. I promise we'll be doing Rust or Zig, but right now we are limiting ourselves to assembly script. So yeah.
So you have to implement it, but you have to use Vim.
Yeah, exactly. So
Make it a little bit harder.
So let's maybe create some kind of function we want to have in WebAssembly modules. The example one we are having in the examples already does Fibonacci. So I'm thinking of something really creative, like
Factorial.
plus 10, which actually takes a number and returns a number incremented by 10. What's cool about assembly script is that's a very cool tool to create a simple WebAssembly modules. It's essentially a TypeScript, but with additional types. So you cannot use number because it's too broad and too vague. You need to specify what kind of number type it is. So I have this here, this simple function that just adds 10. And maybe remove this confusing comment. And what's cool about it is that it actually creates inside the browser a very simple assembly module that I can, copy and paste, or so-called borrow. So this is what WebAssembly looks like in textual format.
So it's like a stack machine, right? Stack-based machine.
It's a very advanced calculator, yes, and it uses a Lisp syntax. So that's the nerd dreams. Yeah, so a very simple module. You see like 12 lines, even like 11. So what I'm going to do is I'm going to copy this WebAssembly text format. I'm going to open my IDE with my examples, and I'm going to copy it here. So I'm going to create a new file. Let's call it +10.vat. The extension used for assembly textual format. And yeah, I'm pasting it here. What I need to do right now is to compile it to binary format. So the way I can do this is to use the WebAssembly binary toolkit. I can close the server. And here in the directory where I have this module, what I'm going to do is to do vat to WASM tool, and I just specify +10.
And this is an external tool, right?
Yes, this is an external tool that you can. It's called WebAssembly Binary Toolkit, and it's essentially a toolkit. It's a collection of different tools to manipulate WebAssembly modules. You can strip it, you can merge modules, just like a linker does. I think.
But that's not something that the users of your library need to use. Like they just need to generate the WASM file. You just went through the source code, so you generated it yourself. Okay.
Yes, exactly. I'm going to show you let's imagine that I'm having this module here. Like I was provided with this +10 module. Sorry, it's not this one.
Not this file.
Yeah. So I was provided with this binary file, right? So if I want to use it in my application, what I need to do is to go into the CLI, go to the path where the example app is. So this is like a React Native app. I just pasted it here, I have this +10 WASM. And what I need to do is to just run Polygen generate. Oh, live demos. I love it. Yeah, so it's empty because
Empty file.
when, yeah. So I need to rerun again because I messed something up. Let me see if it's empty. Open in binary. Yeah. So now it looks like it's not empty anymore. So that's it. So let's go back. I just pasted this module that someone gave me. I'm in the example app. So you see I have this package JSON here, Babel, Metro. So essentially a React Native application, right? What I do is like Polygen generate. And it's forced me that the file that I was using was changed externally, which is a good thing. Let me just remove it. Maybe just run it here. Yeah, so I can just force it because I can overwrite all the files. As you can see, it processes every WebAssembly file found in the source tree. It generates bindings, so like trampolines between JavaScript interface and this web generated code. And when I did this, I will be able to run it in the native code. So let's do this. Let's do this and go to. Oh, I need to obviously pod install because the native code changed. So I need to regenerate the Xcode project. So I need to run pod install again.
Can you show the generated C file just so we know how it kind of looks like?
Sure. I will do in a second. I will just switch the Xcode. And as you can see, running pod install also runs pod Polygen generate. But because everything was up to date, it was taking less than a second. You just check whenever everything is up to date. So you can run Polygen generate even of the already generated code. It won't regenerate, so it's cool. Right, so now I've generated the code and I should have this native code, right? So I can open the Xcode to see what it looks like. And I have my workspace here, right? So I see two external pods here. The first one is React Native Polygen, which is essentially a runtime that contains everything written by us to make it happen. And we see React Native WebAssembly host. So this is like a pod project that contains mostly generated code. So here we'll have everything generated so that the code that is from WebAssembly is a native one. So when I open it, I can see that I have my +10 folder here, and you can see what it's was generated here. So there are some quite few files. First one is related to linking. Right now we only support static linking, but it doesn't really matter. Yeah, you can see it's really C code. It's not even C++. It's just a C code here. There's some like file function declarations here, some struct declaration. I would say mostly low level. You can see implementation. So this is the file along with this one that was generated by WASM2C. As you can see, there's a lot of, it's essentially bringing WebAssembly instructions into C. So yeah, a lot of definitions, a lot of wrappers.
Wait, this was a function with one return +10. Wow, what's happening here?
Yeah, because it essentially translates WebAssembly to C. So if I can search for +10, you can see this is the function type. Yeah. So this is the function that we wrote. So this is +10. essentially that's it. That's the generated code. There's some checks for, you can alter how the code is executed and generated. So there's this, compile time checks whenever you want, traps, exceptions, whenever you want to use long jumps, or you want, to use segu, or whatever is pronounced. And yeah, so this is just a simple wrapper here. Let's see what's under this implementation. And yeah, that's exactly what the function was generated and how it looks like. It looked like this in assembly script. It looked like this in WebAssembly textual format. You can see you get a variable, get a const, and just add them. And I would say it's pretty similar. A lot of it is compiled, optimized out by the compiler, but yeah, still faster than spreading or just them compilation.
Whoa. I wonder, can you later, maybe after you finish walking through the demo, copy the whole thing to Godbolt Compiler Explorer and see the generated assembly code? Okay.
Later. So yeah, this is the generated code, and yeah, we got a bit of topic here. Yeah, so you don't care about it that much. I just I actually need to update my example so I can run it. So I need to go back here, and let's maybe just copy one of those examples. Maybe this one. Let's see. Yeah, I'm trying to copy. Let's call it +10 example. Right. So what we need to do is to actually import the WebAssembly if we are not using fetch. So right now I'm showing you how you can use it with Metro support, because we are also having this plugin for Metro. So you can import those WebAssembly modules using Metro. So you can do +10 WASM from it even suggests me. So is the path all right? Yeah, it's all right. So what it does is that under this symbol, I am having like some kind of unique identifier for this module. So now I can do, I don't really need this. We just quickly simplify it so it's not really that noisy. Yeah, so what can I do? What I need to do is to actually compile it. So first thing to do is we actually compile it. So we need to pass it to WebAssembly.compile, which will create a. This is a bit noisy because we are doing like a multi-step React component here, but you can also do it simple way without it, but this is for the purpose of it being pretty on the UI side. So maybe let's just simplify it even further. Just write this WebAssembly module, const instance, equals new WebAssembly instance, and we need to pass imports. So this way I can just skip it all. And yeah, so what I need to change. I can remove this. I can remove this. Remove this. Remove this. Yeah. So here I'm having a text input where I can actually press type a number and compute the result. So maybe let's call it +10. I can hide the styles. So yeah, the example is still pretty short, I would say. Number text. Okay, and I need to change it to +10. So here I'm actually executing the function. So on the WebAssembly module instance, I'm calling .exports.+10 and passing the number. And yeah, that's it. I hope it works out of the box. I also need to add it to the list of examples. So I think it was here. Oops. Need to do more. All right, so now we need to wait a bit.
So the reason why you have like that instance that exports is because that's how you use WebAssembly, right? It's not that you have to add something.
Yeah.
It's just like how WebAssembly is used on the web.
Exactly. I'm thinking whenever there is some like simple example here. Yeah, this is an example using fetch. Is there any constructor example? Not really.
There was like in that instance that exports that main, for example, that you.
Yeah, that's those are the parts of the module. So first I created module, then I created instance, and instance, as you can see, takes module as the first argument, the one that we are supposed to load, through network and interpret, and we pass import object, and it does have the exports property. I'm not sure why it's not document. Oh yeah, because I'm on the. As you can see, when you create an instance of a module, you can have exports property that contains everything that the module exports, exactly as the Web API spec specifies. So there is no surprises here. But the trick is that most of the WebAssembly examples show you to fetch the module, then the browser compiles it just in time, and then you have access to it. But we get the benefit that we can essentially compile, create the module and instance synchronously without waiting for it, because it's already there. We don't need to wait for anything really. Yeah, the examples are pretty poor, or I cannot simply find a good one. As you can see here, they load some, instance here, and they also access it through instance.exports, for example, table, which is a table you want to operate on using fetch.
Yeah, so like everything that you're showing should be familiar to people that are that worked with WebAssembly before, and this is like the Polygen module is generating like web compliant spec for React Native.
Yes. And as a live demo, I really hope this does not break, because maybe I could forget something. We can see our example here. You can type, let's say 5, and say compute, and as you can see, it adds 10. And to prove it's not JavaScript piece of code, I can actually go here, go to the generated code, to this function, and I can show you through a breakpoint that it's actually a native code. So I'm doing a breakpoint in Xcode to show you that it's not a simple JavaScript function. And yeah, the JavaScript interface of WebAssembly is not really that straightforward. So if you never really worked with WebAssembly, this can be like, too much for you. But yeah, it's like very broad thing, and you need some kind of intro for it. And yeah, just me to quickly check if it works. Say 8. And as you can see, we are already stepping into the native code of that is generated by the Polygen. So we are getting this sweet performance here.
So something that you could also show is at the beginning, we showed all of the C++ bindings that we wrote by hand to bridge the module basis universal. So there is inside of the +10 folder, there is this folder called there is this file called JSI bridge, JSI exports bridge or something. If you can show it.
Yeah. So except those 2 files that were generated by WebASM2C, the remaining ones are generated by us, among others. So for example, we have this header that actually creates a class that represents this module, because in WebAssembly you can instantiate modules multiple times. So it's similar to you having found the same application multiple times. So you can open multiple terminals in the same executable, but multiple instances. So the same goes here. You can create multiple instances of WebAssembly modules. And what's generated here is this code that, it's a namespace Callstack Polygen generated to avoid any conflicts and explicitly say that is generated. And we just generate this, memories, tables, exported functions. We are bridging, creating the JavaScript versions of it, so you can call them. And that's it. That's simply it.
And also what's cool is that here we are using JSI native state and not host objects, which is like recommended by the Hermes team, and it's faster.
So, we are doing really heavy performance optimizations here. And if there are no questions regarding it, I'm not sure if any of you had any questions. Or is it like this obvious for all of you? Mike, you've been sitting quite quietly for quite some time.
I do have some questions, but I guess my question before I ask my questions is, what's up next in your sort of demo chain?
Yeah, so what's next in my demo chain? I already promised running some Rust module. So I wanted to bring, some sweet Rust crates to React Native. What's else I'm working on, as you can maybe, no, you cannot see it here, but maybe I can show you quickly here, quickly see if I still have it. I think I don't know. I don't have it right now. I'm trying to bring JavaScript core JS through WebAssembly to React Native core, and the same with like SQLite. So the code gen part of our Polygen project already, generates code for JSC.WASM, which is a huge module. I think the generated code spans over 20,000 lines, and it still works kind of. So right now we are currently able to run simple modules, as you can see, but because the toolkit of WebAssembly, the tooling around WebAssembly, like you can compile WebAssembly from Go, from Rust, from Zig, from whatever, mscripting for C. The outputs all differ a bit. So what we are going to do right now is to go through most of those languages and write some instructions on how to run it, to check whenever everything works. The way that the tooling is kind of spread around and is kind of different for every language, we need to check for most of them if we are doing the right thing.
One question I have is regarding the loading of those modules.
Mm-hmm.
So I don't know if you remember, but quite some time ago we talked about WASI.
Mm-hmm.
There is a interface for the runtime, in this case React Native JavaScript code, to potentially provide some pointers to certain functions that you would be then able to call from your WebAssembly. Is this already supported? And yeah, I guess that would be my question. And if yes, or if not, I guess the follow-up question is, how is this then generally done? I mean, it's not like I can compile C module and run it, because there will be no standard library, right? So it's
Right.
pretty.
Yeah. So the way some of the tools do it, I think the mscripting does it this way, is that, for example, if you try to compile SQLite to WebAssembly, it generates this JavaScript glue code. Where you have this function. I think let's call it create SQLite, and then you need to provide the modules like fs random crypto, and it does the binding for you. So you can provide those system methods from, let's call node modules or whatnot, and they will be available to WebAssembly modules. This is not
Okay, so
the
we would have to have them in the React Native environment in the first place. Then we could run that type of WebAssembly module that relies on them without issues. But we have to first load the polyfills themselves in the first place.
That's one way of doing it. Because we are running WebASM to C, you can also implement those methods in, like, let's see, say C or C++, whatnot. You just need to, create the functions with specific names, and then the compiled WebAssembly, like when you compile, let's say, Linux or SQLite, as you mentioned, they import external dependencies like fs, file system random, whatnot. And there's this contract with WebAssembly that the environment provides those modules, right? You can provide them from older WebAssembly modules. You can provide them from JavaScript modules, turbo modules, or you can just as well provide them from native code. This whole part of providing dependencies and linking them all together is like your responsibility as a user of WebAssembly, but you have extreme flexibility of how you want to provide it. The main part you were talking about is exactly this one. When you create an instance, you need to provide imports object, and how you provide those imports is up to you. You can maybe require them from React Native FS. You can require them from the Turbo module, or which is not supported yet. You can provide them with C++ code to completely skip the JavaScript layer for maximum performance.
So theoretically, I can put, like, let's imagine that you want to support Node ABI. If I will put all the functions from Node into this object here, I would be able to call and use Node ABI. Okay.
Yes.
So this is like, it reminds me a little bit of like a shared library where you have the export table and import table, right? You have to provide the imports. Okay.
And that's what WebAssembly is. As you can see, I have an import here, which is like some kind of, maybe let's quickly go here and show you src. I'm going to decompile example.wasm.
But there is no dynamic linker in WASM. You have to do everything yourself.
Yeah, you are the linker more, but you can merge modules ahead of time using WebAssembly binary toolkit. You can merge them and optimize away. But let's see at this example. You can see this module has an import, and it's expected of you to provide an add method add function in host object that is of type 0, which is actually, it adds 2 numbers. So there are 2 numbers in, 1 number out, and is expected to provide this method however you want it. And it exports the Fibonacci method, right? And I think it's here, right? Or was it, let me just quickly see. Where was it? It's here, yeah. As you can see, I am creating the imports object here, which provides the add method in a host object as exactly what the module wanted. That's one way of doing it. This is the simplest way, I would say. But because we are using WebAssembly and WASM2C toolkit, this is a bit advanced right now. You don't need to know this. We have this example module here, which was generated. As you can see, the generated code expects you, as you can see, import host add. It expects you that this function exists somewhere. And this is where Polygen comes in. It creates this function for you and calls it to JavaScript interface, but nothing stops you from implementing it yourself here, somewhere in your code, and it will just work. It will be just as you would call a native C function. So there's limitless way of doing it, and this one, well, what I'm showing is a bit advanced, but it's extremely fast. So I'm talking about this because this is one way of doing VASI, as you Mike mentioned. You can essentially just alias some methods like fopen here, or fclose from C or whatnot, anything and environment related. And when the WASM2C kicks in, it just expects that this function exists, because whenever the WebAssembly module calls host add, this function will be called. And however you implement it, you can alias it to standard library. It's up to you. You have extremely limitless options here for maximum performance.
Makes sense. I guess another question would be, I understand from the very beginning of the demo, the way to load this is through this WebAssembly API, which is, I guess, done for the sake of familiarity rather than necessity.
Yes.
I guess the answer is yes, but I guess it would be possible to write some sort of a Babel plugin that would let me just write import path to the WASM file on my file system, just like I import any file, without writing all that sugar code. I mean, we could essentially generate that for the user anyway.
Yeah, we could do this. Yeah, exactly. There's one thing I'm thinking about, but I do not want to spoil it because it's like a potential thing that will be extremely cool for the upcoming version. But I just don't want to spoil it, but it's kind of related to what you just said, that we can simplify it even further, which I agree. We can make it even simpler to use.
Spoil
Yeah.
it. Let us know what's the feature.
That was the
Yeah,
spoiler.
I'm not even sure if it's possible. Okay, I'll just spoil it, whatever, is to actually have this syntax. So, okay, it just collapsed my code. So instead of, maybe let's just open this code here. So instead of doing this, so I can, instance.exports.+10 do this thing. I was thinking about doing the sexy thing, which is import +10 from +10 with imports this way. It uses the with extension of import statement. So it was essentially created for JSON imports, but you can place anything here, and the same goes for asynchronous imports. So you can do this, I think. So you can do the same with dynamic imports. So this way you don't need even to use WebAssembly interface at all, and it will just behave like any other module.
That is very sweet,
isn't it?
And sexy.
Yeah.
So that is one of the things that you're working on, or I guess at some point you could work on from the DX perspective. What about like the sort of loop needed for the developer to sort of write WebAssembly and see the preview inside React Native instantaneously? How long is this process? I guess it is not as quick as fast refresh.
No.
Probably I should have WebAssembly library already ready, so I can just work on running it inside React Native. And is there any plan on making that even easier, or like how would you even like approach it? Does that even make sense to make it compilable, let's say, together with, like, let's say the WebAssembly was compiled each time you would make any change, for example. I know it's stupid, maybe not, but the idea would be that I would see the changes almost instantaneously. I guess that's not the case today. How far are we from that, and is that even a possibility in the future?
Yes, I think so. It is. That's one thing I mentioned before, is that way forward we are thinking about having WebAssembly runtime interface akin to JavaScript interface. This way, with the same interface, without any changes to your code, you could, for development purposes, use like a runtime that does interpretation, or like just-in-time compilation, which is disallowed in App Store, but would be a great fit for the developer case, where you can reload the WebAssembly module, so you don't even need to generate code to do ahead of time compilation or whatnot. But you can just update the module, the app would reload it, compile, either interpret it or compile it just in time. So you can have this sweet and sexy hot reload. But right now we are only focusing on release and performance of the application. But it's possible. I would say it's possible. We are not closing the doors.
I think you can also compile it to a dynamic library and watch for modifications and reload the DLL or like shared library.
Yeah. Right now we are only supporting static library, but we already have this interface for it, and we only need to figure out the plugins like Cocoa, Postgre, or whatnot. And in one of the future versions, we want to support dynamic linking. So when you do the essential like compile streaming and it returns a promise, that's the moment when we actually load the dynamic library. So yeah, it's all in the future.
Let me ask you a very uneasy question now. What about out of 3 platforms? Because this you showed us on iOS. I guess this works exactly great on Android. What about other platforms?
It's transparent to it. Like, it's a sandbox. I think it even helps them, because if you create the WebAssembly modules, I think it's easier to provide support for WebAssembly modules on, like, I don't know, Windows or any other platform you dream of, than to support native C++ code. So it's a win-win.
Great.
Nice. So I guess if the best way to experiment with Polygen, if we were to show it to everybody, is and I think we briefly went over that. Maybe it is worth going through this again, unless it's already well documented. But I guess the best way for everybody to experiment with this would be to have the WebAssembly module ready, and then they can just put it inside React Native and run it. So where they can get those WebAssembly modules from? One way is probably, like you said, to compile it. And I think we have went over that. But maybe there are some, awesome WebAssembly collections that that you maybe have used already, or I can use, like, beyond just sharing the code across different platforms. I'm sure there are some interesting things like this Postgres implementation in WebAssembly that we could potentially have fun with. Anything that comes to your mind, or any resources that we could potentially use to play with this?
I've used some WebAssembly. Just that. It lists all the libraries and whatnot.
Sounds like a very typical repository name. I'm sure it exists.
Yeah, yeah, exactly. And I also asked ChatGPT, so it just points out the pretty cool libraries that are already compiled to WebAssembly. So the possibilities are endless. But a small heads up, some of them are actually a bit outdated. So if you're trying to use them in React Native, first make sure that they are not outdated. And, if they are, it will be easier to maybe you do the compilation to WebAssembly. But most of them are actually pretty fine. So yeah.
That makes sense.
So, what would you say would be the future of this? Like, obviously, getting it to the full spec compliance, like having all the features with WebAssembly. Let's say it is implemented today, and what's next? Like, after going with,
I'm not sure if the answer world domination is acceptable in this context, but that's one way of thinking about it. So everything is done this way. I just want people to use it and have no issues with it. Really, if some mad lad wants to, as we already talked, run Linux on WebAssembly in React Native, you should be able to. So yeah, if that ever runs using Polygen, I'm more than fulfilled in my life, really.
Okay. So, like, do you plan, because now you showed us that like you drop in WASM file, you generated the bindings, and you have it in your library. And at the beginning you said that you want this to be a replacement for, like, not a replacement, but a different tool that you can use instead of turbo modules, let's say. So do you plan to have it work in a way that you can ship libraries with it? So
yes.
This is
yes.
Something on the roadmap, right?
Exactly, yeah. One thing on the roadmap, which is actually we want to support the WebAssembly system interface, WASI. So this way, most of the languages actually work out of the box, like, standard libraries and whatnot. So this is one way of bringing about the goals. One of the goals is if you want to write a turbo module in Rust, in Zig, or Aldo and whatnot, and if something compiles to WebAssembly, you can already do it in a way. At least when the Polygen gets more stable, you will be able to do. So if you want to do any modules in other languages than C++, then it should be easy with Polygen in the future, for sure.
Mm-hmm.
Okay,
can you talk directly with other turbo modules? Like, is it something on your own as well, or they have to be completely isolated?
Not sure. It's hard to say right now, but I would say they have to be isolated. But yeah, there's one way of working with different languages. You have some other under the hood, don't we, Mario and Mike?
Yes.
Yeah.
But
So we are actually we are actively exploring this area.
Okay, so it looks like we are almost out of questions. Like, is it possible?
Wanna go through the God bolt through the assembler code, see how the add 10 functions or like plus 10 inlines?
I'm not sure if it will, emit it without the whole runtime, because I need another files for it to be there for it to compile. So it won't be just a 5-second operation.
Okay, then later.
So like, how can people contribute to the project? How they can help you with getting to this goal of like shipping 1.0? And what would even mean to get to 1.0? Because you shared like a roadmap maybe for even a few years of development, but
Yeah,
like the next goal probably would be to get to 1.0,
Yeah.
have it a stable library.
Yeah.
So what's missing? So like, can people use it tomorrow if they want to,
Not
or should
really.
they wait?
So my general advice is right now, if you're very if you're like a beginner in WebAssembly and you're not a veteran, it will be better if you just wait out a bit, because the experience can be a bit rough. But if you want to hack around it, if you're like, you like WebAssembly, you like React Native, it should be very easy for you to use it and even contribute. But there are some rough edges, which are expected because we are not, stable at 1.0. On the way of going for a stable version, I think the stable version would be if we support like the WebAssembly modern spec completely. So like WebAssembly 2.0 with the usual extensions that, most of the people use, so that you just can use, I don't know, Rust WebAssembly bindgen. The output just works without any modifications. So the goal is for it to be completely, maybe not completely, but mostly transparent. So you don't need to know a lot of internals right now for it to work. It just works out of the box and it's completely transparent to you. That's the goal of it being 1.0, really.
I'm sorry, I don't know if I got it, or you didn't answer. Maybe the answer is no. But is there like, if I wanted to help you, what I can help you with? Unless the answer is nothing because it's so low level and it's only me and maybe Mario that can help you.
Okay, so regarding contributions, there is this README that shows what is supported and what not. So the first thing that, like, on the journey to contribution would be to test it out on different modules and see what breaks or what doesn't break. If anything breaks, like reporting an issue is a good contribution. Even like implementation of some kind of features is also a good contribution, because right now we are not full, even like WebAssembly 1.0 compliant. And yeah, so in the future, also some kind of tests, maybe documentation, which is like work in progress right now. So there's a lot of things to do. I think that there won't be any kind of issue of missing tasks. Mostly just like the openness and like willing to contribution is a good way to start.
So you mentioned this, like you answered this partially, but like, how far are we from the spec compliance so that people can reliably use it in their apps?
That's a tough question.
Like, how many, maybe not reliably, let's say, how many functions do you need to still implement, like, to have the compliance? Like, is it a few hundred functions that are missed
No,
from the spec, or how big the spec even is? Because I have no idea.
As in spec, I'm more thinking about consuming the WebAssembly to see output. So like for example, exceptions, right? So right now we do not support exceptions, and WebAssembly to see does support exceptions, but you need to enable them, I think. And then in the source code, you need to point the code where to throw the exceptions, for example, and stuff like that. So more about this, look at the specification, see how it should be done, see how WebAssembly2C does output it, and just simply create a beautiful bridge between JavaScript interface and WASM2C. How many part of the specification? I would say we are close to maybe, without any extensions, I would say close to 80%. Really, maybe 90, I'm not sure. We are missing some tests, which we are working on creating extensive tests for it. We have some basic prototype there, which is not public yet. And regarding extensions, yeah, hard to say. We should be good enough for the pre-alpha, let's say, of 1.0 without much of the extensions, but ideally the most common one, which I'm not sure which one really are. I think they're like exceptions, ref count, and maybe garbage collection in the future. But yeah, it's all about what is used the most and what tools output which features.
Okay. So I could still use this project even if I don't have even if it's not at fully compliant level, because if, for example, I have a simple module, that would just work, then I can use it. So the reason why it's not getting to like a stable version would be just because of the compliance, right?
Yes.
It wouldn't mean that it's like totally unstable, but rather than it's just not compliant. Okay.
Exactly.
So I think the short answer is just give it a test drive and give us feedback to help to prioritize which features needs to be implemented first.
Yeah, exactly. If you have any ideas of any plans, any things you want to try, feel free to contact us. Any WebAssembly modules you're dreaming of having in your React Native app, just hit us up. We are willing to help you.
And PR's open, right? If they will implement some exceptions or something.
Of course, always.
Nice. So I guess we're awaiting the remaining 20% for it to be completed.
Yep.
And meanwhile, we will have to try finding some more interesting examples for you. Maybe I can eventually end up running this Cobol stuff that I wanted, provided I can figure out the WASM bridge, which does not seem to work, but we'll see.
Yeah. I think you need to build it in like a Docker container because it's like so outdated, the tooling. So
yeah, it's a mess.
Have you noticed that on Twitter, like on X now, there is a lot of movement that you can compile Docker containers to C, so you can have an executable that runs the Docker and everything. So you got a full circle, like you can have a C app, put it into Docker container, build the Docker container as a C source code, compile it again.
I didn't know that you can build like C code from Docker container. That's pretty cool.
Then you can build Docker containers as WASM and run it on the web.
Yeah, I think I would say with WebAssembly, which is a good sandbox enough. Docker seems to be like a overkill for some cases, but yeah, whatever fits.
So I think we should definitely do another live stream sometime soon on WebAssembly to check in how the project is doing and if you are at 100% compliance yet.
Yeah.
And yeah,
I already promised Burak the Rust demo, so yeah, I need to do it right now.
I have for the next live stream, I do have some topics, unless you guys have better ideas for next Monday. I have reanimated V4 with CSS animations, Expo router, and React server components. That would be the second one. And the third one, I wanted to try one.dev by Nate, which is also very interesting because it uses Vite, which is interesting. So these three I have on the roadmap, and also this one, for some reason, I assigned to you, Oskar, which is with the Apple tool that I have in my office. Maybe you mentioned that you were interested in helping me get it up and running. Because we
I didn't, but I can help you.
Yeah, I don't know how we get the screen sharing of the Apple II, but maybe we need to have a separate camera just so that people can see everything that happens on the screen. So we just have to pick something for the next Monday, but rather than that, that one will also happen eventually.
So yeah, if anyone is interested in some of those topics, make sure to join us next Monday.
Exactly.
Yeah, I think we can wrap it up, right? So thanks guys for joining me this time and presenting Polygen. And yeah, I will see you next week.
Thank you, Oskar, for hosting, and thank you, Robert, for the demo, and everybody.
Thank you, Mike. See you.
Thanks.
Bye.
See ya. Bye.
Bye-bye.